So this section on Earth's early history, we have to paint a picture of what Earth was like for us to understand the changes that have occurred over the last 4.6 billion years. So at 4.6 billion years ago, and I'm going to read this next section to you. I usually do that for the drama, not high drama. I just like to emphasize. So I guess for the emphasis, I'll do it. We do have to understand that life has only been here for 3.9 billion of the 4.6 billion years that Earth has been here. So some significant change had to occur leading up to life arising on the planet. And even at 3.9 billion years ago, Earth was very different than it is today. So I'll just jump right in. Geological and astronomical evidence suggests that Earth formed as pieces of cosmic debris collided with one another. Cosmic debris is space debris. They collided and combined over millions and billions of years. Then two very large rocks. I know I'm not reading right now, just bear with me. Two very large rocks, about the size of Earth and Mars, approximately, collided. And what's left from that collision is now Earth and the moon. This has nothing to do with Mars. I'm just telling you, two very huge rocks collided in space. And so much heat was released that the globe melted. It's usually at this point, if you can envision, you take your hands and instead of rubbing them together like this, just kind of slide them one time really quickly. And you feel the heat in your hands, and that's kind of an analogy for the friction that would have been created, except the size of Earth and Mars. A lot more heat, right? So, second sentence. While the planet was young, it was struck by one or more huge objects. This is what we're talking about. And the entire globe melted. So now you're talking about Earth that is a liquid rock. Every portion of the solid rock has now melted due to the heat from this collision. For millions of years, violent volcanic activity shook Earth's crust. And remember, the crust was very, very thin at that time. Even now, it's thin in comparison to the diameter of the Earth. The crust, you've heard this analogy in earth science, where if you cut an apple in half, the crust is about as thick as the skin is on an apple when compared to the Earth. It's about 40 miles now. At this time, though, you imagine liquid rock, the crust begins to form millimeters at a time, and then it's feet, and then it's hundreds of feet and thousands of feet, and then, 40 miles is 250,000 feet or something like that. So, okay. So the entire globe melted. For millions of years, violent volcanic activity shook Earth, and we could add thin crust there. Comets and asteroids bombarded its surface. That's one of the conjectures as to where water may have come from. About 4.2 billion years ago, now that's 400 million years after Earth formed, right? Earth cooled enough to allow solid rocks to form. So for 400 million years, Earth was hot enough that solid rock could not form. At the very surface, it was beginning to, but we're talking about density. We're talking about solid rocks feet across, okay? And at 4.2 billion years, when solid rocks were forming, it wasn't long after that where the Earth's atmosphere fell below the temperature required for water to condense from water vapor. What temperature is that? In Fahrenheit. It's 212 Fahrenheit, boiling point, 100 degrees Celsius. Once you get below that, Earth will condense the water, okay, under these pressures. That's why I say Earth. Earth's surface became stable enough for permanent oceans to form. But guys, the water didn't form here. It was brought from somewhere else, and that's another portion of the discussion that we can have when we meet next time we do class. This infant planet was very different from Earth today. Earth's early atmosphere contained little or no oxygen. It was principally composed of carbon dioxide. That's not a harmful gas to us, except that if in its presence it can suffocate us. It's not, the gas itself is not bad. Water vapor, yep. Nitrogen, most of our atmosphere is nitrogen now, with lesser amounts of, these are harmful gases: carbon monoxide, hydrogen sulfide, highly deadly, and hydrogen cyanide, highly deadly. Oh, hello, full screen. If you had been there, a few deep breaths would have killed you. Because of the gases in the atmosphere, the sky was probably pinkish orange. You know that the sky is sort of bluish now because of what? If you said refraction due to ozone, then you got it correct. As the light passes through ozone, it gives us that blue appearance. And because the oceans contain lots of dissolved iron, they were probably brown, so pinkish brown. This is where life begins on Earth. See if I can move this guy out of the way. Just minimize it. Let's add a page. This is what we're talking about. If you look at your desktop of the presentation, this is kind of the best image I could come up with years ago of what we're talking about. Brown oceans, pink sky, pretty gnarly stuff. So, of course, we have questions on how this may have begun, right? So Stanley Miller and Harold Urey in the 50s, the 1950s, tried to perform an experiment. So you have to follow the bouncing magical pen. Doop, doop, doop. Okay, I'm going to start over here. What we're doing here is heating water like we would understand that Earth was very hot, right? And water, when it gets heated, evaporates, and then it flows through this unit. They've added here methane, ammonia, hydrogen, trying to simulate what Earth was like. Then in here, sparks of electricity, right? Where'd that come from on Earth? Lightning. As this is allowed to cool, the water condenses. Some of the heat is let off this way. This is something you could see in a chemistry lab. And what we're looking at in this little condensation chamber, they're pumping cold water in around, and then the cold water comes out, and it cools the hot water into cold water that falls in here, and it gets reheated and then back up through this way. But the condensate is then captured, and what they were able to accomplish was a mixture, and it says here, of organic and other compounds, okay? Acids, amino acids, organic compounds. So they made some of the constituents of life, but as it says here, they were close but not accurate. All right, so it's a novel approach. They did something neat. His son picked up the experiment years later and came up with some more information, but we still have not been able to generate life from these conditions. It's just our understanding that life began under these conditions. That being said, we cannot, and this is a theory that's gaining more ground, we cannot overestimate the possibility that life came from somewhere else on a heavenly body, some sort of meteorite, okay, could have landed here, or a comet carried from somewhere else through space, right? So those are some of the constituents of life, but then we go into life's origins, which the constituents don't get us there. It's like Legos on the ground. They don't just spontaneously form themselves into a car, right? So these proteinoid microspheres, this was the precursor to the cell membrane. We know that it had to exist. These are not alive, but they do have selectively permeable membranes. And the fact that we're seeing that on Earth now can tell us that it could have happened again. Just like we find fossils from the past, we presume that today is related to the fossils of the past. So the things that are happening today are related to the past. So inorganic matter combined into simple organic molecules, make bits of RNA nucleotides, and then these three questions here. How did life begin to self-replicate? Again, that may not have happened here. It may have. We don't have evidence for this. So it's biology's role to talk about these things and to experiment and to grow. And, you know, we've answered questions in the past that we didn't have answers to when the questions began. So we might be able to do that again. You should be able to click on that movie. It's one of those awesome movies I show you. Yeah, go ahead and watch that one. Just pause this video and watch it. And then, you know, we can talk about that one when I see you guys. All right. Another huge thing. So temperature had to drop, water had to form, life had to form, but life formed in the presence of a very low oxygen environment because life is responsible for creating the oxygen. So it was very anaerobic. So appearance of oxygen actually drove some life forms to extinction because they couldn't exist right? But now we know that oxygen in the atmosphere allows animals to thrive, okay? Another huge step, eukaryotic cell origin. So if you remember, we saw the evolution of life in 60 seconds earlier in this presentation. So these are the big events that we're covering here as we go through today. 2 billion years ago, we first see the eukaryotes. That's less than half of Earth's history ago. 2.3 billion years ago would be half. So this is within the last 50% of Earth's history. We get prokaryotic cells, internal cell membranes. Remember that a prokaryote doesn't have this. So the prokaryotic cells that were developing this were the earliest eukaryotes. Other prokaryotes can enter these cells and live symbiotically. And now we're talking about the earliest of the eukaryotes that are photosynthetic, which is going on over here in this little diagram I'm scrolling with. Pull this up. So we're talking about here, photosynthetic bacteria, aerobic prokaryotes become the mitochondria, photosynthetic bacteria become the chloroplasts. These then shoot off into plants, and these shoot off into our animals. And this was a theory that came up. The endosymbiotic theory was with Lynn Margulis in 1960. So again, it's a theory. It makes a lot of sense. We don't have a whole lot of evidence behind it because this type of evidence is microscopic and soft. And then I've talked to you guys about this all year as we went through evolution. Sexual reproduction, huge, 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 right? This allows diversity. With every meiotic division of gametes, there's a new possibility. And you guys are now well-versed enough to understand that evolution thrives on that diversity. The differences between organisms allow these competitions to be won by one group or another, okay? So shortly after the appearance of eukaryotic cells, sexual reproduction came along because there was multicellularity and cell specialization. Many cells with some specialized just to the role of reproduction. Greater diversity in offspring, no longer an exact copy. Give it a few 100 million years, and we've got that multicellularity I just talked about, which is huge. Okay. So this will be due on obviously on the due date when I give it to you, but you're going to do this guy here, okay? And then we're going to, let's see. This is probably something we can do together. So let's try to do this together on WebEx. I'll see if I can run it from my screen. We'll see how it goes. And then we're going to watch this movie. So you're going to watch this at home. So we're going to finish up 19.3. The next class will be doing this together and having our meeting, our discussion about chapter 19. I'll then assign this to you, and then you're going to take your test. So when you're coming to this, we have a class here and discussion. Then you have a day to do this, and then we'll take the test live the following class. All right.